Hi, kids. Hey! Thanks for going back for number 3. This is the Modern Unit Review Part 3. Now, remember, the modern unit is really 3 parts. First part, hey, even though we said light was a wave, light is actually behaves like a particle. That was photoelectric effect, Compton effect, de Broglie, all that stuff. Second part was photon emission and absorption. Third part is nuclear physics. So we're going to talk about like the nucleus and nuclear decay and stuff like that. So let's get into that. So first, the word atom. When scientists first came up with like, hey, I think particle like matter can be broken down into little pieces, and they're like, oh, the smallest piece is we're going to call an atom because the word atom means essentially the smallest piece. And then they didn't realize that you could break an atom into parts, and then they found that an atom is made up of electrons and protons and neutrons and all kinds of stuff. So, it is important. One of the things you need to understand is this idea of what is a fundamental particle. Fundamental particle. Okay. A fundamental particle is a particle that you can't break down into smaller pieces. So if you think, oh, well, that's going to be, and that will be, a proton, and a neutron, and an electron. You're 1/3 right. That's an electron. An electron you can't break down into smaller pieces, but protons and neutrons you can. You break them down into quarks. So a proton is actually made up of smaller pieces, like you can take and break apart a proton. And a neutron is also made up of smaller pieces. They are made up of what's called an up and a down quark. And there's other quark names. They're very quirky, hence the name quark, like a strange quark and other stuff like that. But for our purposes in this class, you just need to know up and down. So a neutron, which is going to be like this, okay? We're going to write it like this because it has no charge, and it has, as far as like our elementary mass units, it has 1 mass unit, okay? So it has no charge like this. Well, it is made up of 2 down quarks and an up quark. It's easy to remember because a neutron has no charge. It is a dud. So it's made up of down, up, down, where a proton is like this, okay? It has a positive charge, and it has 1 elementary mass unit. An electron has a negative charge, but even though it does have mass, its mass is so small, we say it's 0 as far as elementary units, because compared to a proton or neutron, it's really, really small, essentially 0. A proton is actually, it's not a dud, it's 2 up quarks and a down quark, okay? Now, how do you get the positive charge? The positive charge comes about because this is positive 2/3 charge, positive 2/3 charge, negative 1/3 charge, negative 1/3, positive 2/3, negative 1/3. So a down quark actually has negative 1/3 of our elementary charge. So if I go negative 1/3 plus negative 1/3 plus positive 2/3, I get nothing. So hence a neutron is neutral. Where if you go positive 2/3, positive 2/3, that's 4/3 minus 1/3, that's positive 1. Hence a proton has a positive 1 charge. Okay? So, and you might be more confused, but if you want to review that, that's fine. What you need to know for this class is that a fundamental particle or an elementary particle is one that you truly can't separate. Okay, you can't break down to smaller pieces. And a neutron and a proton are made up of quarks. A neutron is a dud, 2 down quarks and an up quark. A proton is not a dud, 2 up quarks and a down quark. Okay, an electron is an elementary particle. It's a fundamental particle. You can't break it down to smaller pieces. Okay, all right. There's our basis there. So then let's talk about what actually happens if you have nuclear decay. Now, a couple of things with this that I want to kind of go through with you. So I have my beautiful, I love golf. So I have my golf ball model of an atom. So let's say, I don't remember what I did in other videos, but we're going to say that the red are my protons and the white are neutral, are my neutrons. Okay, so if you were to count, I have 1, 2, 3, 4, 5, 6, 7 protons. So that would make this a nitrogen nucleus. Okay, and I also have 1, 2, 3, 4, 5, 6, 7. I think I have 7 neutrons. So this atom would actually be nitrogen, if you look it up on the periodic table, and it would be 14, and it would have a periodic number of 7 because it has 7 protons, okay? And it has 14. This number here is telling you neutrons plus protons. So this is telling you the number of nucleons. Okay, a nucleon is just stuff that's in the nucleus. Okay, so the number of nucleons there's 14. This is telling you the atomic number, which is really the number of protons. Okay, so this has 7 protons. There's 14 nucleons, which means, hey, that nucleus has 7 protons and 7 neutrons. Now, you might be, well, why are there neutrons there in the first place? Well, here's why, okay? So what actually happens if I was to kind of draw this, the nucleus here. Let's say I have 2 positive charges. This would be helium, okay? Do these 2 positive charges want to hang out next to each other? And the answer is, well, no, because positive repel. Well, there is a fundamental force called the strong nuclear force, and I'm a physicist, so I don't know tons about chemistry. I know basics, but the strong nuclear force is strong. It's stronger than the electrostatic force, but it only occurs on a very small scale. In this case, the nucleons have to be touching each other. Now, with my model, you can see it's held together by hot glue. The hot glue you can think of as the strong nuclear force. Like, that's representing the strong nuclear force in my model. So if you take a look here, these 2, they want to repel, but they're held together by the strong nuclear force. And this is still stable just by itself. But if I add a neutron here, it is now actually more stable. Why is it more stable? Because this neutron doesn't add any more electrostatic force because it's neutral. It's not trying to repel stuff, okay? But it does add more strong force. Do you see how there's more strong force here and more strong force there? It would be like, if you look at my model, okay, do you see how my golf ball, right here, okay, do you see how there's going to be strong force here, strong force there, strong force there. But if it's neutral, okay, it's not supplying any more electrostatic force. So that the reason we need neutrons is to make our nucleus more stable. So in fact, if I wanted to make it more stable, I would do this, which is why this element is the one you find most common in nature. Why? Because it's the most stable of all of the different heliums, okay? But what's going to happen is as you get more and more stuff in your atom, that your atom can become more and more unstable. So if I have lots of positive charge, I'm going to reach a point where these positive charges repelling each other is going to overcome the strong force holding it together, and then my nucleus is going to decay, hence nuclear decay. So it's going to break apart. And there's three main types of nuclear decay that you need to understand. So I'm going to briefly go through those three main parts. They're super easy to understand. In fact, you want to see them on the AP test because it should be free points, okay? So the first type is called alpha decay. Okay, remember an alpha particle is just a helium nucleus, which is this, which is what I just drew for you, which is that. So what actually happens with alpha decay? This typically happens if you have a really, really large nucleus, okay? Like uranium, for example, lots and lots of protons and lots of neutrons. If you have a really large nucleus, what happens is, so like if I have, you know, this really, really big nucleus, and if I kept on drawing, you know, more and more and more stuff here, okay, again, you get the idea that what's going to happen is, if this is unstable, I would get this come out plus whatever's left. Plus some more energy, okay? But this is like my alpha particle, hence my alpha decay. So if this is my original element, which sometimes you'll see this as, it's just random element X, okay? It has a random atomic number of Z. It has a random atomic mass of A. Remember, atomic mass is the number of nucleons. If it decays, you are going to get this helium, like an alpha particle, which is really this. Well, that means this new element, here, I'm going to do it like this. This is my new element. It has to be A minus 4, and it has to be Z minus 2. So literally it decays into a new element plus this, plus some energy. And the energy is typically in the form of a neutrino. Sometimes you'll see it as like a symbol like this. So just if you see it on the AP test, that's what they're talking about, is just, hey, you have some additional energy that's left over. But pretty simple. If, you know, a lot of times they'll give you an element and they'll say you have alpha decay, and they'll ask you to find this. Just think about the equation, and this plus this has to add up, this plus this has to add up. Easy peasy, okay? The other type is beta decay. Okay, a beta particle, I don't know why they call it a beta particle, I guess alpha beta, but a beta particle is just an electron. And here's what happens in beta decay. Beta decay, a neutron, which remember is this, okay, decays into a proton, which remember is this, plus, well, wait a second. If this is 1, this has to have nothing. If this is 0 and this is 1, this had better be -1. Well, guess what that is then? Oh yeah, that's going to be an electron, which is also a beta particle, I don't know, plus some leftover energy. Okay, and again, you might see a neutrino. Now this typically happens for smaller nuclei, like let's say you have carbon-14. Carbon-14 is C14-6, okay? Carbon-14 is a naturally occurring element in our atmosphere. It happens when high energy photons from the sun hits the nuclei up there, and it causes this to happen. I'm not a chemistry teacher, but this nucleus is unstable. So what happens is you end up with, if I do in general, and then we'll do it this way, A and Z. That what happens is my new element, okay, if you look, if one of these is decaying to this, my new element has to go up 1. So this would be Z plus 1, but you'll notice this stays the same, plus my electron, which they'll say is a beta particle, but I'm going to say plus an electron, which is 0, -1, and then plus some energy. Okay, so that this is decaying to here. So if I have carbon 14, it's going to decay into nitrogen plus my plus that, which is going to be my electron plus some energy, which is going to be -1, 0 plus energy. Sorry, I'm running out of space, but you get the idea, okay? That's beta decay. And then the last one, so just so you guys have it with beta decay, so here's really what's happening. Beta decay, one of these neutrons is turning into a proton and an electron, okay? So it's like, hey, my nucleus still has the same number of nucleons, but it just has one more proton, okay? And then the last one is called gamma decay, and okay, and gamma decay is really only happens if you have something like a nuclear explosion, something like super energetic. My nucleus, okay, has lots of energy, okay? And if you were to think like your energy well, like we did with the photon absorption and emission, okay, but with a nucleus, where these energies are going to be way, 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 way bigger, you know, like millions of times bigger, this is going to decay to the same nucleus, okay, with less energy, plus a gamma ray. And if you remember, gamma particles, okay, have way higher energy, way bigger frequency, you know, and hence this is like the basis behind the Incredible Hulk and the superhero stuff like that, where, you know, the Hulk, Bruce Banner was, I think it's Bruce Banner, was hit by gamma radiation and that caused him to mutate and turn into the Hulk and whatever. But you get the general idea. Gamma ray. There you go. Okay. Those are the three different types of nuclear decay. The other thing I just need to mention to you, just so you have it, is actually two more things. We need to talk about half-life. Okay. Half-life. Let's say I'm going to make up, and let's say I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 radioactive nuclei, okay? Half-life is the amount of time it takes for half of these to decay, okay? So like if the half-life is, I don't know, let's say 3 days, okay? Or let's say 4 days. Let's say we're gonna say our half-life is 4 days. What that means is if I start with 10 nuclei, after 4 days, 5 of these, actually I'm going to make it 12 just so I'm going to have even numbers. But so if I start with 12, then 6 of these after 4 days will have decayed. Okay? Well then, after 8 days, okay, half of what's left will decay, so that you would have, so these 6 have already decayed, and then now those 3 would decay, and so on, that after each 4 days, half of what you're left with decays, okay? That's what half-life is. There is a formula for it, and the College Board, for whatever reason this year, wants you to understand what that formula is. So let me just write it down and make sure you have it. The formula is saying this: N equals NO E raised to the negative this times T. Okay, so here's what this is. This is not wavelength. I know it's confusing, but this is going to be our decay constant, which is actually also equal to the other equation, which is natural log of 2 over the half-life. They do half-life like this. So the decay constant would be natural log of 2 over half-life. So if ours was 4 days, you could figure out what that decay constant is. And then this equation just tells you how many you're left with. So if I start with 12, if I plug it into this formula where I know my decay constant here and I plugged in 4, I could figure out how much I'm going to be left with that. So, but this honestly should be just plug stuff in and make sense out of it. Sometimes you'll see this in terms of kind of, they'll go like this. They'll say the number versus time. So for ours, it would be like, hey, we started with 12, and then when I got to 6, so if I start with 12, when I get to here, like with my graph, this time would be my half-life, which for us, we said was 4 days. And then when it continues to decay, when I get to 3 molecules left, this would be 8 days and so on, but that's what your graph looks like. Okay, and then this would eventually approach 0, but it would never actually get to 0. That's half-life. Hopefully that makes sense. And again, you guys aren't expected to know tons with it. Just kind of be able to use the equations and understand what it is. And then the last thing we need to understand is this idea of mass defect. And I think this is pretty cool. So here's what mass defect is saying. So I have my nuclei here, okay? If we were to take each individual neutron and each individual proton, okay, an individual neutron and individual proton, you can look up the mass of them. It's on your constant sheet here, okay? But if you were to look up each individual one and then you were to add them up, so like if I had, let's say, I think we said that was 6 and 6, or maybe it was 7, I think it was 7 and 7. So if I took 7 protons and I add the mass of 7 neutrons, you could figure out what that adds up to be. But the crazy part is, okay, when you actually combine them like this, that the mass of this nucleus would actually be less than the mass of the individual plus this and this. So then it's like, well, wait a second. How is that possible? Where's the energy going? And this is where you have to think of Einstein's famous equation, E equals mc squared. It's going into some energy. So there's some energy holding this nucleus together. And how would you figure out how much energy that is? Well, you would figure out how much mass got converted, like your mass defect, hence that's why it's called mass defect. This change in mass, whatever that change in mass is, times the speed of light squared, speed of light's pretty big, will tell you how much energy is going into holding this nucleus together. And guess what? That amount of energy that's holding it together, if you can overcome that energy, you can break this apart and cause nuclear decay and stuff like that. But hopefully that makes sense. That's called mass defect, or that's the same thing with fusion. You know, in a star, what is happening? So hydrogen, if I have hydrogen, which is typically maybe just this is H12, okay? And I fuse these together. If you were to add the mass of a hydrogen, 2 hydrogen atoms, so like these two, if you were to add those 2 up, okay, you would get a number. Well, if you look at the mass of helium, which is this, you're actually going to get a smaller number than this. Well, what happened? In a star, gravity causes these things, gravity is so strong, it causes these things to combine and fuse together. Well, that extra energy then gets released as light, as HF and stuff like that, according to this equation. All right, there. I am finally done with modern. Bye, kids.